Okay, well, good morning, everybody. We are the official Ferrofluid group. I'm Justin Howe.
I'm Santi.
I'm Austin Haas.
I'm Kevin.
I'm Tiger.
And we did our project on stabilizing buildings using a tuned mass damper using ferrofluids.
So, what is a tuned mass damper? Basically, a tuned mass damper is a device that helps cancel out the motion of an object. The biggest real-world application of this is put in buildings to help mitigate movement from earthquakes and swaying in the wind. We have a diagram of a mass damper, one that works well and one that doesn't. And the one that doesn't, you can see that the mass is stationary. It doesn't move, it doesn't swing, it doesn't have much motion. The one, however, that's free, as it swings in one direction, the building sways in the other, and the forces cancel each other out, and the building stabilizes faster. In the real world, these take shape in the form of giant steel balls, usually, such as this one in Taipei 101. It's a free damper, and it helps to mitigate earthquakes and wind sway. There's some shortcomings of these big balls, however, because they weigh a lot in order to be able to mitigate movement of such a large building. The ball weighs about 292 pickup trucks, and at the top of the building, that's not something you really want hanging above your head at all times. So the way that tuned mass dampers work is they use momentum. Momentum has two components, mass and velocity. With the big Taipei 101 ball, it has a very large mass but a very small velocity. It only moves about 3 centimeters, even during a magnitude 7 earthquake. So what we were wondering is if we could acquire the same results using a large velocity and a small mass using ferrofluids.
So ferrofluids are a liquid that contain iron nanocrystals. And what's so interesting about these nanocrystals is that they actually contain magnetic properties when in presence of a magnetic field. So what this allows us to do is to control their direction and therefore use it as a dampener. And of course, what we would lose in the mass of the giant steel ball, we would gain in an increase in velocity.
So let's talk about the mechanism here. You guys still remember what we're talking about all the time? Momentum. So momentum equals mass times velocity. Well, here we use velocity. We increase velocity using solenoids. So how do solenoids work? Take a look at this. Well, when a current is going through the wires, it creates a magnetic field. Well, ferrofluids, they are fluids when no magnetic field is applied to it. But if there is one magnetic field that is applied to it, it acts like a magnet. And also, solenoids are magnets. So, you know what happens when two magnets meet each other. Let's say that the tower is leaning towards the left side. We switch on the solenoid on the right, and then, swoosh, all the ferrofluids goes that way. Well, you know, the motion, it moves with velocity, which creates momentum. Will counteract the momentum of the leaning building. And then, you know, it goes back that way because, you know, this movement. So let's turn on the one on the left side. Well, it goes again. Through this process, we will counteract the momentum created by the tower leaning on both sides. And also we can control it. Well, that is where we place the ferrofluids damper. Normally, the traditional ones, the gigantic steel ball, they always require space up to like 10 to 12 floors. But this one, it only requires 1, which greatly saves the space.
So in order to prove that ferrofluids have the capability of stabilizing buildings, we decided to make some calculations. So first we have to find the momentum created by the giant steel ball. So the mass of this ball is around 660,000 kilograms, or that's around 730 tons. And as for the velocity, we found some recordings of the ball swaying during a magnitude 7 earthquake, which is a pretty big earthquake and requires a lot of momentum to stabilize the building. So we're setting ourselves pretty high standards here. So we found that the velocity is around 0.03 meters every 2 seconds, which translates to 0.015 meters per second. So using our momentum formula, we multiplied the mass times the velocity and found that the momentum created is around 9,900 kilograms meters per second. So let's say hypothetically we have around 1,800 kilograms or 2 tons of ferrofluid. We're already eliminating around 99.7% of the original mass, which amounts to around 26 dump trucks. So that's a lot of weight we're losing right now. So what does that mean about the velocity? How much velocity would the ferrofluid need to reach in order to match what the steel ball, in order to match the momentum of the steel ball? 100 miles per hour? 1,000 miles per hour? No, we'd only need 12 miles per hour or 5.5 meters per second. Now that's more than half of Usain Bolt's max speed. So, and also another comparison is railguns, which use similar technology using magnets and whatnot, and they can reach velocities of around 2,400 meters per second. So this shows that ferrofluids definitely have the capability of matching the steel ball and also have the potential to be even more efficient and maybe even stabilize buildings during magnitude 10 earthquakes or something of that sort.
All right, so let's get into our actual experiment. So first we started out making ferrofluids, as you can see from the other groups. We mixed the FeCl with FeCl2 with FeCl3 with ammonium hydroxide, and we made the iron nanoparticles. We then basically mixed them out with water and ethanol, which basically made our ferrofluid, which you can see right there. We then took this ferrofluid and we put it in basically a glass test tube so we could see it moving around. So you can see we put the glass test tube with the ferrofluids inside, and then we also have these things called solenoids on the left and right. Basically what these are, it's just copper wire that we wrapped around the glass test tube. And basically we would take this, the copper wire, and we connect it to these batteries, which we had 4 Duracell batteries taped together, because that's what we had. And the ferrofluid would go from side to side near the solenoids when we turned them on and away, since when we turned on the solenoids, it created an electromagnetic field, which would attract the magnetic ferrofluid. So we actually have a video of that. So you guys can see.
Yeah, all right. So as you can see to our right, the video of the results of our experiment. As you can see, when the solenoid is turned on, the fluid tends to kind of group up near where the solenoid is, demonstrating that we can control the fluid. Here we have another video where instead of using the solenoids, we used more powerful cube magnets. This kind of shows that if we have a more powerful magnet, you can control the ferrofluids even more strongly than we can do ourselves. So these results, what they mean for us is really that we demonstrate that we can move the fluids at what we estimated to be a speed of about 0.125 meters per second or 0.3 miles per hour. This is important because now we know that we can for sure generate some momentum using our ferrofluid. The ferrofluid has a mass, and we just demonstrated that we can give it a velocity. And if you remember the momentum equation, P equals mv, you would know that we now have a guaranteed momentum. This means that we can, in fact, use this ferrofluid to stabilize buildings, because if you can put momentum into the ferrofluid, you can use that momentum to counteract the momentum of any swaying building. And we have done all this in maybe 12 or less hours of work. So if you imagine giving us a larger time frame, how much more we could do.
So yeah, as we were talking about, if we had more time, we could definitely do a lot more, and also if we had a lot more funding as well. So you see, our solenoids, it's literally just copper wire wrapped around a test tube. If we actually had an industrial level electromagnet, it would be much more powerful, obviously, and it would do a lot more work in creating an electromagnetic field and actually pulling more ferrofluids faster from side to side, as well as a battery. We had 4 Duracell batteries taped together. Obviously, if we had a real one in a building, we'd have a much more powerful industrial quality power supply, which would obviously, again, make it much more stronger, make a lot more fluid move faster, and ultimately make a much better product.
So basically, with a super bootleg setup, we managed to actually get results in moving a fluid and measuring its velocity. So if we can do that in just 6 hours of prep and 6 hours of experimentation, if we had days, even a couple months, we could definitely get that up to 5 miles per hour. We're at 5% of our goal of what we need to just match. And since we have railguns, which use basically the same technology in a slightly different way, railguns go very, very, very fast. And that would make ours, that could very well exceed the standard that we set with the magnitude 7 earthquake in the steel ball.
And let's talk about the future of this project. Well, as you can see, these are the world's 10 tallest buildings, and all of them have a damper in it, which means that we've got market, very large market. And you know, the land that are usable these days, they aren't sufficient, which means that the buildings must be higher and higher. So yeah, we've got market. Anyway, I wonder whether you've seen a advantage of using these, because when you are using a traditional gigantic steel ball, you can just place it in the center of the building and it barely moves. But using ferrofluid, it can be as long as the diameter of the whole building, maybe like 50 meters or 60 meters. Well, that is highly efficient. Also, I would like to mention the computer program, because we're using computer program to calculate how much voltage should be applied to each solenoid, and which solenoid should be activated and which are not. So with this, we can precisely control and we can precisely counteract the momentum of the leaning building, which means that it's more stable. And I think that's it for our presentation. Thank you all.
No, that was not taken into account. But of course, it could be calculated. We just didn't do it. Sorry. Could you repeat the question? Yeah, definitely.
I wouldn't think so, but because the magnet itself isn't really moving, it's just controlling the ferrofluids. So the ferrofluids.
So it would be heavier. I definitely think it would add weight. But as you can see, I mean, we were cutting off 99.7% of the weight. So even if we did add it up, it would still be tremendously have less weight than what the normal steel dampener had. Yeah. If you want.
Also, adding on to that, is worth noting that with the 730-ton steel ball, that's just the weight of the ball. There's also mechanisms that are used to actuate. There's pistons and controls for that, which we didn't take into account for the weight of steel ball. So there's extra mass on both sides, really, but we're just comparing the mass of the actual components that are used to affect the momentum.
And also, I would like to talk about some statistics. Normally, the weight of a skyscraper that above 600 meters, it weighs about 1 million tons. Well, compared to that, 2 tons of ferrofluids, well, you can just forget about it. But the momentum, it is very, very large.
So the question was, how exactly would the computers be able to control how the ferrofluid is moving within? That could just be used with gyroscopes or whatever to sense if the building is tilting one way, and then that can start the mechanism to calculate how much ferrofluid to move in what direction in order to counteract that movement, which is more of an engineering problem. We were mostly focusing on a proof of concept. So the question was, how exactly do we measure the speed? Truth be told, fluid dynamics are kind of hard, so we kind of eyeballed it and we gave it a pretty rough estimate, but it wouldn't be like much less or much more than that, than the number that we use in our calculation. So it's relatively accurate, but of course it's not perfect because fluid dynamics are hard.
Can you explain a little bit more about how you measured it? I know that you had a video before of the ruler there. Can you explain that process?
So the question was how exactly calculate the velocity. So basically, we measured the point from basically where the fluid was bunching up when the solenoid was activated. And then we calculated the time from when the solenoid was activated to when it was all more or less settled. We used that time, and the velocity we used was about half the test tube. That was the distance that we used, because that's, again, a pretty rough estimate for about how much, on average, distance the fluid covered. So the question was about how exactly the mechanism would work in like a real world application. So what we sort of visualized was a sort of pipe system where there's pipes going in all sorts of directions, so you can exactly pinpoint what direction, or not exactly, but have a pretty controlled direction of which way you want the force to go. And also the way that railguns work is there's a long series of magnets that are activated and deactivated in order to force an object out at an extreme velocity, which is what computers would be able to do in our system.
And please. The question is, would like to be a series of tubes or just one tube on the same floor? Well, I would like to say that if necessary, we will like put like different tubes on different floors. But actually, I think one rotator will be enough. It can rotate in different directions, and computer program, they can be precise. They can be like turn in east for 0.00001 degree, and it will perfectly match the momentum we need to counteract.
Does the altitude make a difference in the ferrofluid nature in the way it works?
The question was, would the altitude of being up in a tall building affect how the ferrofluid works? And I assume yes, but then again, we're not exactly sure, but it definitely could, it definitely could not. This is mostly a proof of concept to show it can be done, and there's more work to be done in this area.
I'm just curious. That's like maybe the instructors have an answer for that.
Most likely it wouldn't. Depending on the liquids, you could always have it sealed in a system, so if it has a high vapor pressure, it wouldn't matter. They would actually probably be using oil with a high density, so it would be fine. Especially since most of these buildings are still designed for humans, so as long as the humans